Jim Linnemann, or in case you weren't here last week, uh, is a retired physics prof from MSU and a PhD from Cornell. And he's had a lot of experience all over the world doing his gig. And it's exciting that we can hear about some of that today. And it's a real pleasure. Help me welcome Jim Linnemann.
Go better. All right. That's our place. Plan for today. I'm going to start off actually with a little bit of a refresher. There's a nice video from the Gizmodo website when they did a visit to HAWC, and so I'll play that for you. Now, I'll talk about how it is that we go from this really low-level information of a time and a number of photoelectrons to reconstruct the direction and the energy of the photon, which hit the atmosphere, 15 kilometers up. And how we make sky maps, because after all, making sky maps is my definition of what makes a telescope, right? You can make a picture of the sky, it's a telescope. We don't use focusing of light like many of the telescopes you're used to seeing. That's why HAWC looks so different than usual telescopes. Then there's also another little gotcha. I like photons because we can do astronomy with them. However, 99.9% or 99.99%, depending on the energy, of what we trigger on is actually cosmic rays. And if we want pictures of the sky in TeV light, we need somehow to be able to get down to the photons. That's a challenge. And then from having done those as the preliminaries, I'll talk about how it is that we do science, what kind of observations we do, how we publish our work, how we collaborate to do our work, and then I'll get into some specific studies that we've done, and maybe a little bit about the plan for the future. Now, I think you've all made an excellent choice for celebrating Pi Day. And my wife has kindly provided some Pi Day stickers for you, so you can pass these around. I think the technical people have passed this around. This is my other references slide at the end, but there's a paper copy for those who have the privilege of being here in person. So could you pass that around? And the first reference on that is this book on the constellations and beginning astronomy, which I had the extraordinarily good fortune of having as a high school student. It's a really good book. And you may remember that somebody recognized the font. That's because this guy who wrote the book was the author of Curious George. And he applied his visual skills to making the constellations look like their names. A really nice book, and there's excellent reference material in the back. By the way, I can't help but salute Gordon's sartorial choices. What a fine shirt you're wearing. Excellent choice. Of course, I didn't make all these slides from scratch myself. Some of them I did, but a lot of my colleagues who've been giving talks, I selected from those. So we have a big web page of all the public talks that people have made. So first, let's look at the Gizmodo video.
This is one of our photomultiplier tubes. This is all vacuum.
Can you take a picture of me with it for my mom? Near the top of a mountain in rural Mexico sits an unconventional telescope looking at the highest energy light from outer space. We paid a visit to learn more about this unique lab. Particle physicist Ibrahim oversees much of the site's day-to-day. We met up with him to learn about what HAWC does and how it works.
I'm Ibrahim Torres. I'm the site manager of HAWC. This is the biggest gamma ray observatory in the world. Behind this altitude, the particles start being absorbed by the atmosphere. So that's why we need to be close to at least 6,000 meters.
Why don't the clouds block out the cosmic rays?
These particles cannot see the cloud. That's one advantage of this kind of technique. It doesn't matter. The particles cannot see the clouds. You can imagine that each of those tanks are like a pixel of a camera that is taking 25,000 pictures per second of the sky.
The HAWC Gamma Ray Observatory turns the idea of a telescope completely on its head. HAWC records the highest energy particles and light from outer space, called cosmic and gamma rays. These rays could come from supernovas, galaxies with bright centers, or other crazy cosmic phenomena. The cosmic rays first hit the atmosphere, which sets off a chain reaction and turns them into a shower of lighter particles with less energy. Each tank contains nothing more than liquid water. The particles are traveling at nearly light speed through the atmosphere, but the speed of light in water is only around 3/4 the speed of light in space. So when they hit the water, they create a cone-shaped flash of ultraviolet light. It's basically a sonic boom, but for light instead of sound. Sensors at the bottom of the tank can see the resulting flash and turn it into a signal for a computer. HAWC can determine what the cosmic ray was made out of, its energy, and where it came from by measuring flashes and combinations of flashes through the tanks. Alberto and Brenda have worked on HAWC since the beginning. They both were instrumental in getting the laboratory off the ground from its conception over a decade ago until now.
It kind of grew out of a project that we had at Los Alamos National Lab. So we had all these ideas how to make a better detector, which involved going to higher altitude.
Great advantages of these water tanks is that these modular. You assemble a few, and then you can show that this is going to work.
It allowed us to prove that this was actually a good place to build and then to get the funding for the full detector.
Brenda took us to the field beside the experiment, which is dotted with new, smaller water tanks currently being added as part of an upgrade. There, we watched scientists install one of these tubes.
So this is one of our photomultiplier tubes. It converts the photon to an electron. We're just now getting it operational.
Awesome. All of the photomultiplier tubes are hooked up to computers in the central counting house. Every particle's flash comes with a timestamp. They combine all of the water tank data to determine cosmic rays' origins.
Well, first, let me just show you. This is the sky as we see it. With our detector, we can see a wide field of view. This is an animation that showed how our detector gets hit. The dots showing up, those are signals in our detector. So we can tell precisely where they actually come from.
Which is awesome. Brenda showed me the computers that combine all of the signals from all of HAWC's tanks. This results in the data that scientists can actually use.
So we have 1,200 photomultiplier tubes, and all those signals have to come into this one room.
So that each one of these wires represents one of the water containers?
Yep, so the signals came in the other one side of the board, and now they come out as digital. We replicate this a bunch of times, we collect all the data, and then we send it to a bunch of computers.
So if something crazy happens, this will already, 4 seconds later, this will already be ready to say, everybody point your telescopes here if you want to see the crazy thing that happened.
Right.
Scientists store the data on disk arrays, which they drive in beer coolers to Mexico City weekly. There, they load the data online and transfer it to the US, then onwards to the rest of the world. The transfer can take up 1/4 of the total bandwidth between the US and Mexico at around a terabyte of data per day. Manuel grew up in Atzitzintla, close to the lab. He deals with the site's high altitude daily.
Y tú sabes, a esta altura la cantidad de oxígeno en el aire es menor. Entonces tienes que aprender a regular tu cuerpo, aprender a moverte y compensar esa falta de oxígeno. Usualmente digo que cuando bajamos, y yo digo que me siento algo así como Superman, porque como tu cuerpo compensa la cantidad de oxígeno necesaria, por alguna razón te sientes mejor físicamente. Es una zona rural y el 90% de las personas se dedican a la agricultura. Muy pequeño no tenía yo idea de que existían lugares como estos, pero aún así no me imaginaba yo estar en ellos. Cuando mucha gente en el país puede crecer estudiar y trabajar en su lugar de origen. Y yo creo que soy de los afortunados que han hecho eso.
Raul oversees a national park that includes both the Sierra Negra and Mexico's tallest mountain, the nearby Pico de Orizaba.
Nosotros estamos tratando de preservar la vida que hay dentro del planeta. HAWC es una infraestructura temporal. Al término del proyecto se va a levantar todo y va a quedar el espacio como estaba. Y eso fue un proceso de negociación que se ha llevado, que seguimos teniendo, cómo vamos a poder hacer que confluyan los intereses de la investigación con los intereses de conservación.
Our planet is just a tiny speck in a grand cosmos full of violent explosions, spinning stars, and other unexplained mysteries. And if we ever hope to understand this vast home, sometimes it takes a few hundred vats of water on top of one of Mexico's tallest volcanoes.
This is one of our
All right. So I'll talk now about reconstructing the showers caused by the incident gamma rays or photons at the top of the atmosphere. Obviously, we use software. We estimate the original direction, and that's done on the basis of the times recorded in the photomultiplier tubes. We also have to know where the tubes were in order to interpret that information, so it's survey information. It also has to be written down correctly in the right units, which didn't always happen. And then we also try to estimate the energy of the original photon. There we base that on the number of ultraviolet Cherenkov photons which were detected by each of the photomultiplier tubes, and again, the locations. And we have a couple methods of doing that. And then we make a map of the sky based on that information. Here's an animation which shows a shower sort of sweeping across the detector. So let's say here's my detector. In this example, the shower comes in from the left and above. It hits this part first and then sweeps through so that the tubes that are hit on this part of the detector are last, right? And yes, that's a level flow. Don't worry, there's a really good deep gully between us and them, so it would have to be much worse to get us. So the basic idea is that you can make a plot like the one here of the time of arrival and the position, and you can see you sort of fit a plane to that, and the perpendicular to the plane is where it came from. Now, there's some finesse about that because, in fact, it's not completely a flat plane, and we have to worry about the curvature of the shower front and other details like that. But hey, that's what software is. So we record a general timestamp on when the trigger was recognizing there was a cluster of hits. That moment of when the trigger happened also allows you to say, well, where is up at this moment as the Earth is rotating around? Then we find the center or core of the shower where it was most densely hitting phototubes. And that's using the locations and the number of photoelectrons. Then we find the best plane like I showed you. And then we add the corrections. And the next thing we do is we drop the hits that don't fit that front, that beginning front of the shower coming down. And then we do some iterations. Another thing we do is we try fitting a second plane with the other hits that we threw away. And then we check to see which of the two planes has the more hits in the end. And we keep the one with the most hits and we throw away the one which has the least hits. And that's because cosmic rays are happening all the time. Even when you have a nice big photon shower, there's nothing that stops there being a random overlap of a small cosmic ray shower at around the same time. And those would confuse things, so we want to get rid of them. So that's a recent improvement we made for the last year or so. And then we sort of loop around them again. And that the shower plane gets turned into we recorded the zenith direction, and then we know what the angle is compared to up. And then we also then translate that into more absolute coordinates, where they are with respect to the fixed stars. Because again, we're on this Earth, which is spinning around and up, keeps moving through the sky. That goes by the term of right ascension and declination. Then when we want to make sky maps, well, you know, we're using the fact that the Earth is spinning to sort of spin us through the various parts of the sky. At any moment, we're looking at maybe within a maximum of 50 degrees off of zenith, either direction, or it's circle around that direction. So that's about a sixth of the sky. But overall, we cover over 60% of the sky from where we are, which is just at 21 degrees latitude in central Mexico. That precision timing allows us to know the angle within a tenth of a degree and keep track of it over periods of years. And our accuracy of pointing, which is plotted down here as a function of a fraction of the number of phototubes hit. Obviously, having more phototubes hit gives us better information. So that goes down from maybe 1 degree at the very lowest, half a degree for sort of moderate size, down to as low as a tenth of a degree accuracy, which is like a fifth of the size of the moon. The celestial coordinates, the right ascension is basically the celestial longitude, and the declination is another fancy word for the celestial latitude. And when I mentioned the sidereal day is how many hours it takes for the same star to come back to the same location in the sky. And that's different than it takes the sun to come back to the same position. And that's because we're rotating, but we're rotating and going around in orbit. And by the time we get back there, there's one less or one more. I can never remember which rotation. So that's the basis of the difference of the length of sidereal day and the solar day. They differ by a few minutes, but you got to keep track of it. And that's, again, the reason that we see different stars at different times of the year in the evening. So, for example, you can see Orion this evening if the clouds go away. So making sky maps is basically saying, okay, I'm going to know where any event happens compared to the location of the fixed stars. And so I gave the example of Orion, and here's it in one view. Here's another view of Orion and its neighbors in this book here, which you can have a look at afterwards. It's a very nice book. Now, if I look at a bigger zoom across the whole sky, well, now you're in fine print, but Orion is over here. So this is just a big Mercator-like map of right ascension and declination. The yellow line here is where the sun and the moon go through. That's the so-called the ecliptic. And the blue with a little green line, almost invisible, through here is the Milky Way, the disk of the Milky Way, which we're sitting in. And in these coordinates, it has this funny curved path. On the other hand, you can choose galactic coordinates, which are referenced to the galactic plane. And then when you plot it, it looks like that. And so that's the center of the galaxy and more stars there. But the Milky Way up in the sky is nothing other than our view of the plane of the Milky Way. Now, as I mentioned, there's a big problem that the photons we want are what we'd call signal, is a small part of what we observe, lots and lots of background. So if I just showed you a map of raw counts, right, you wouldn't see anything because you'd be completely dominated by the cosmic rays, which are almost uniform. To make useful sky maps, you have to first estimate the amount of background at a given location. And that's sort of tricky. But the basic idea is you look, if I'm trying to figure out what the background is in this region, I look somewhere else, either in time, or neighboring spatial locations. We emphasize same location, but different times. And we also, eventually, if you have a bright source there, you might have to exclude that bright source because although you don't want to subtract your signal. Then you subtract that background from the map, and what's left is the photons. And then because there's uncertainty in the backgrounds, even if you know the average rate, you don't know how many happen to be at the time you made this map. There's always a statistical uncertainty in the background. And so we often make maps, which you'll see later, with measuring the statistical significance of a signal, which is the net signal after some background subtracted divided by the uncertainty of the background. So obviously we can do all that, but it would be much better to reduce the amount of background first. So I'm going to show you a couple of brief videos about how it is, the basis on which we do them. What I'm going to show you is some simulations of remember I talked about the big showers that happen in the sky, and there are two classes of showers we're interested in. One, which is initiated by photons, and they have some characteristics which you'll see. And then the other one is the cosmic rays, or the hadrons, or charged particles. Now, what you will see in this video for the gamma rays is that it's completely dominated by blue particles, which are either electrons, anti-electrons, or photons. In particular, there you will see no yellow muons because I've simulated a pure photon shower, no random overlaps. And then the other stuff, you basically don't see many of those either. Okay, so here, let's just look at a movie. What you imagine is you're lying on the back at HAWC, looking up at the sky. And what the graduate student from many moons ago did was he took the simulations and looked where particles were in such a shower as a function of depth into the atmosphere, right? But he mapped that into time, which makes sense because the power shower starts up here and then propagates down towards you. This video goes down to the depth of the Milagro experiment, which is about, so I'll stop it when it hits the altitude of HAWC. Blue dot in the middle. Now there's some action. Start to see particles produced, but the center is where almost all the particles are. So it's pretty heavily concentrated. Now here at 10,000 meters, that's way up there, where airplanes fly. 7,000 meters, 6,000 meters. Whoops. You do it differently. Here's around 5,000 meters. Here's 4,100 meters where HAWC is. Geez, it's messing with me. Where is it? Yeah, I'll just let it run. That's HAWC's altitude. And this is what's left at Milagro. You notice it sort of faded out. So Milagro had a harder job than us because it was at lower altitude. Okay, but anyway, that's the characteristics of the showers. There's lots of fluctuations. There's lots of particles. We only happen to intercept some fraction of them, only the ones that rake it down to our altitude. And there are these fluctuations, but it's pretty concentrated in the middle. Now here's the same thing. Okay, now I'm going to do the same thing for a proton of the same energy starting a shower. This is more like what happens when a cosmic rays. And in this one, you'll see a much larger variety of particles. And in particular, of interest, you'll see yellow particles, which are muons. Muons are are good at penetrating down towards the Earth, and they're one of the telltales that this was a hadronically induced interaction. Pow, popcorn, right? Muons flying off. We're about to have another interaction shortly. Bang. Much more dispersed. Now here's a secondary center off the other side because that one got a lot of energy. It's not nearly as centered up in the original position. The secondary centers, again, we're producing more muons, 10,000 meters. Five, 6,000 meters. 4,000 meters HAWC. And what's left at Milagro's altitude. So, in fact, for Milagro, detecting something as low as 2 TeV was pretty tough because there's not a lot to work with, right? So we're better at higher energies because there's more particles to it. So those differences that you see are the key to how we tell whether a shower that we observe was photon-induced or cosmic ray-induced. And unfortunately, there are, these were chosen to be reasonably distinguishable. But there are fluctuations in showers. So a perfectly hadronically induced shower could be dominated by pi-zero particles, which decay into photons, and therefore it looks an awful lot like the electromagnetic shower. And similarly, the hadronic showers are so wide that good hunks of them might miss the HAWC array, but you might have some subset which looks like an electromagnetic shower. And those outriggers will help us tell those cases. And then similarly, gamma ray showers also have overlapping hadronic showers. We try to get rid of the hits from them, but there are muon hits, and if a muon goes close to a phototube, it really lights it up. So that's one of the things we're going to try to key on. So again, here's sort of the transverse view of the shower with hadrons, more fluctuations, broader. Here's the sort of a radial view of a photon-induced shower and sort of a 2D view of it up there. So the kinds of things that we use in practice is we make a chi-squared, a goodness of fit test between the expected shape for a photon shower and the set of hits that we observe. That's probably our most powerful discriminant. And when I say expected, what I mean is simulated in our software of making lots and lots of such events and saying what they look like and what their fluctuations look like on the average. At lower energies, we use a peculiar sort of a variable, which is looking basically for a tagged muon, a single phototube, which is pretty far away from the center of the shower, but has a huge hit, lots of photoelectrons. And that can happen if here's the phototube and the muon managed to go right through one of them. So the simulation includes everything we know. Unfortunately, it also includes some things we don't know quite so well. But it simulates the shower physics. And it also simulates our understanding of the response to the particles that make it to the ground by our detector, by our water, and by the phototubes and the electronics. Here's this overall result of where we wind up. On the left is how the signal fares. This is the fraction of the signal. So we choose cuts nowadays. The solid lines are require that we keep 60% of the signal. We have to give up some of the signal in order to get rid of the background, right? But that's where we tune the cuts. In the case of the background, with higher energy or more hits, the fraction that pass keep falling and falling and falling. Now, if you're only lighting up a quarter of the tubes, you still pass 10% of the background. But at higher energies, you pass Well, here with about 50% of the tubes hit, you pass maybe 1%, and at very highest energies, it's even 1/10%. So we do a pretty good job when we have enough to work with at rejecting those. And a nice number, remember I said our significance is the signal divided by the uncertainty in the background. And that can be as much as a factor of, well, above 10 when we have half the tubes lit, and as much as a factor of 40 or 35 or 40 at the very highest energies. So that's the result of getting into the background 20 times, 30 times as much statistical significance for the same number of starting photons. Now, we also tried to reconstruct the energy. There, we're trying to deduce the energy of the initial gamma ray. And we do that based on the number of photons we observed, where the PMTs are, and the total number of PMTs hit throughout the detector. And the simplest amount you can do is, I think somebody just suggested even last time when we were chatting, was how many PMTs are hit. That's a pretty basic variable. And obviously, if you have a more energetic shower initiation, you'll have more of them hit. There are more sophisticated methods, including one we developed at MSU, and those are based on the radial profile of the shower. We sort of saw a picture of the radial profile. Well, you can do fits, assuming that, and try to figure out what's going on there about the radial profile compared to this core of the shower. So this is what my student did. He picked a number of variables. Some of the variables, like zenith angle, well, geez, why would you include that in a neural network? Well, actually, it's used to correct, because depending on where the particle was in the sky, if it's far from zenith, it had to go through a bunch of atmosphere, and therefore you have to make a big correction to its estimated energy for the fact that a lot of it was absorbed. So there's things like that. And then also just a fraction of PMTs is one of the inputs to it, but it includes all these things. And then the fraction, depending on the radius from the center of the core, sort of bend up and use that. The performance, here you can see, here's the correlation plot of the reconstructed energy versus the true energy. And again, at high energies, correlation becomes tight. Here's what would have happened if you'd used the fraction hit. Well, first, it's much broader. Second, it has this nasty characteristic of sort of turning over and saturating at high energies. Because, well, when you set all the photo tubes off, or almost all of them, there aren't that many more to catch. So it doesn't behave as well as you might like. And he summarized the performance here. Here is the uncertainty of the estimate in this axis, and here's the energy of the photon, again, according to our simulations. That's what would happen if you use the F-hit estimator, which has this sort of funky dependence. We had an older method, which was, let's see, yeah, that was the green was an older method we'd used. And the two new methods, of course, the best one is the one we made at MSU for the purple, right? You knew that already, right? The outriggers will improve our sensitivity because they're out there at the areas out the edge of the main array, and they can detect if we have a big, wide hadronic shower lighting up a number of the tubes there. So that's going to help us, and it probably will increase the sensitivity by about a factor of 4. But we don't have all the software working yet. It's important for us to estimate the sensitivity of the detector. So, for example, here's some 3 lines for HAWC. This is the first 3.5 years sensitivity. This sort of says, well, how much flux would it take to be sure that we've detected something as a function of energy? Higher energies we're more sensitive to, but on the other hand, the spectrum falls off drastically, so those are harder to get. But we are better than the existing detectors once we're at high energies. If we include the outriggers, then the sensitivity increases by this amount. We also often compare ourselves to these Cherenkov telescopes. They are much more sensitive than us at low energies. And they're also, but we're better at seeing extended objects, which we'll talk about in a little bit. And so there's some trade-offs between which one is which. Now let's talk about making science. This is around 100 people, more give or take. There's, of course, a rotating cast of students come and students go. I pointed out some of the people I've worked with most closely. There is Ibrahim, you saw in the video. So he was hired as a young postdoc, but somehow they saw in him, okay, this guy can be in charge of making everything work, and he's good at it. And one of his students came to MSU for a year and learned neural network techniques from us. And now he's a senior postdoc at UNAM back in Mexico. This is one of our postdocs who's now a faculty member. Time passed between this picture and now. This is Alberto, who was also in the video, one of the key people who said, well, let's move this thing to Europe, up to Mexico, and here would be a good place to build it. Here is my colleague, Kirsten Tollefson, who is the lead professor on HAWC now at MSU. She also, like me, had a background in experimental energy physics. Decided to work with me. Here's Michael Schneider, our cantankerous engineer with whom nothing would work. He's demanding because he wants it to actually work. This is one of our previous spokespersons at Michigan Tech. This is the principal investigator in the US, where most of the money flows for the detector, Gordon Goodman of the University of Maryland. This is Brenda Dingus of Los Alamos, who you also saw in the video. That's me. Here's Andres Sandoval, who is another of the people in Mexico who helped decide where it should go. And finally, Maria Magdalena Gonzalez, who was the next office to me as a graduate student when I was doing my sabbatical at Los Alamos. She is now spokesperson of HAWC. And it would not be in Mexico but for the fact that she is from Mexico. She went to the US and became a student of Brenda at the University of Wisconsin. And yeah, so Magda is one of the key people. She in fact recruited the other senior people, say, we can do this in Mexico. But it takes a bunch of people to make this thing work. A typical publication might have 80 or 100 authors. Instead of fighting about the order of who's the first author and who's the last author, we do it alphabetical, because with 100 people, it would never converge. We all have the option to sign any paper which we have read, which we agree with the result after having had a chance to comment on it. And we take the effort to certify that we read it and approve. We have to sign up. That leads to some very frustrating software, but that's another story. HAWC has produced 72 papers. We have another 5 or 6 queued up, which could be ready to go soon as we release the so-called Pass 5 improvements. The way it works is each individual paper represents somewhere between a half a year and 2 years of effort by a team of 1 to 3 people. The 1 people probably involves some supervisor. Sometimes is really split across several people's work. Then each paper is reviewed by an internal editorial board of 4 people inside a HAWC. I've been intimately involved with that process. And before submission, the paper, after passing the editorial board, revisions to all comments, answers, yes, I agree with that. No, wait, this is why you're wrong when you complain about that. Then it's opened up to the entire collaboration for comments. for a two-week period. And the author has to respond to those comments. And our goal is that we've given the paper the business before it goes to the journal. So that the journal, we hope that in general, the journal reviewers don't have a hard job of dealing with the paper which hasn't been carefully looked at. And there's typically one or two external reviewers before publication happens. This is sort of the life cycle of a publication. We also collaborate with many other observatories. We have formal agreements of sharing data prior to publication with a view to doing joint publications for this long list of other observatories. And that's sort of important with how we operate, because these people have different views of the same data and contribute things that we can't, and vice versa. So some of those are triggered by us seeing something like a new candidate list. Some of them are follow-up observations. Sometimes other observatories will follow up on things that we did. If there's a flare in some source, well, everybody's going to jump on it, and so on. So this is the kind of thing we do. So we also collaborate with the LIGO Gravitational Wave Observatory and look to see whether we see anything in our wave band with those as well. So that's one of our big publications with, I don't know, probably 2,000 authors from that elaboration and some of the others. The kinds of things we want to do, we want to look at sources in the galaxy. We want to look at extragalactic sources. We want to look at cosmic rays. And we want to do fundamental physics. Fundamental physics means actually testing laws of physics, whether they're being intended to be intended or making tighten the shoes tests on existing understanding. Multi-messenger means that involving other observatories at other energy ranges. And you can again learn more about a source by saying what kinds of emissions it makes visible by different apparatus. So that sort of covers the general area that we're talking about. Let's do a nice simple one, cosmic rays. Now, I complained that cosmic rays don't allow me to do full-blown astronomy because the cosmic rays are charged and they're bent around by magnetic fields between the source and us. But cosmic rays coming through the region near the Earth, if they run into the moon, they're absorbed. And there isn't really not too much bending in the Earth's magnetic field between the moon and us for this range of particles. So the moon appears to us as a hole in the sky. There's less cosmic rays at the position of the moon. Now we have to track it where the moon is each night, right? But we do that. And you see that the position of the shadow of the moon depends on the energy, which is listed up on the top. Right? And that's because, after all, there's a fixed magnetic field. Higher energy particles are bent less and are closer to the position of the actual position of the moon at the center of this diagram, and lower energy ones are curved more. And we can actually use that as a calibration to make sure our energy calibrations are correct. The sun is harder to find, weirdly enough. And that's because it has its own strong magnetic field, and that does mess up the cosmic rays that are shattered by the sun. So depending on where you are in the solar cycle, the shadow of the sun might be visible or might be very hard to see. I'm not sure if I'm going to have time to get into that, but we do have an example of such an analysis. So fine, we make sky maps. I think I've given you a picture about how the sky maps work. Maybe do people have questions on the part that I've talked about? Because I'm now going to launch into more individual analyses. Yeah. Whoever. You decide, Gordon. Yeah.
I'm still quite unclear about the differences between the so-called gamma ray and a cosmic ray in terms of its appearance.
Yeah.
And if the gamma ray represents a photon,
Yes.
and we accept the fact that the photon can be a particle and behave like a wave.
Hmm.
Tell us more about the composition of the cosmic ray, these charged particles,
Yeah.
and you introduced the concept of a muon, which I thought was a subatomic particle.
It is, yes.
So could you go into the pion, the muon, and why we should be interested in
Sure.
these?
Sure. Okay. So cosmic rays are essentially made up of nuclei of atoms, which have been accelerated somewhere. And that's a question. Where is actually a good question, right? But most of them are protons because, well, geez, hydrogen makes up most of the mass of particles of gases in the universe. There's some helium, there's less lithium, and so on and so on and so on, higher energies, but it goes all the way out to iron, right? So there, you name any particle nucleus that you can find in the world, it's amongst the population of cosmic rays, hadronic cosmic rays hitting us, okay? Now, what do those showers represent? It represents, let's just take the simplest example of a proton. You know, high energy physics people study the interactions of atomic nuclei hit by high energy protons. That's exactly what initiates the shower, the hadronic showers I've been talking about, right? And the classic thing that happens is if you hit a nucleus with a proton, first it knocks parts of the nuclei out, you know, either neutrons or protons, it knocks them out of the nucleus. But sometimes it hits one of those nucleons really hard and it produces new particles. The classic new particle, most common new particle that hits are so-called pi mesons, which are subatomic particles. They have a mass about 1/6 of the, or 1/7 of the mass of a proton. They come in three varieties. Two of them are charged, plus and minus, and ones that are neutral, which is the pi zeros. The pi zeros are interesting to us because they can decay into two high energy photons. So we can detect those also if they happen to be produced. They look like photons to us, right? The charged muons have a decay chain which starts with emitting a neutrino and a muon. A muon is a somewhat lower energy subatomic particle than the pions, right? And muons look like overgrown electrons, but because they have so much more mass than an electron, they don't make showers. They just sort of plow through the atmosphere. And therefore, they can get down to the ground where we are, and they might hit our detector and make a noticeable signal. So we're quite interested in muons because they only happen when you have one of these hadronic interactions. They don't happen when a shower is initiated by a photon. So that's the basis on which we tell the difference between the showers.
This is a question from a non-physicist.
So, okay.
In the video, one of the scientists was explaining how HAWC worked.
Yeah.
And he explained that don't worry about clouds. Gamma rays can't see the clouds.
Yeah.
And then later in the video, they talked about I guess photons were slowing down
Oh,
to
okay.
75%.
Oh, okay.
And
Yeah.
I didn't, and first of all, does light only travel at 186,000 miles per second? Or is that the maximum speed?
That's the maximum speed. That's what it travels in a vacuum. It travels very close to that in air because air isn't very dense. When you put it through glass, it bends the light because it slows it down. The slowing down bends the light. That's how these things work, right? Lenses work that way. In water, it's slowed down even more. It goes down to about 3/4 the speed of light, because when light tries to propagate in water, there's always another atom that hits and another one that hits, another one that hits. So the collective effect of all those collisions is that the net wave of light that travels goes only 3/4 of the speed of light in vacuum.
It ricochets its way down.
Yeah.
Right, those that aren't absorbed.
Yeah. Yeah.
Back to the pion. If the neutral pion can dissociate into two photons, how does a photomultiplier detect the photon that came from a hadronic shower as opposed to a gamma ray shower?
They look just the same. That's the trouble, right? So that there are pi zeros produced in hadronic showers. And if the hadronic interaction happened to fluctuate to have most of its energy in a pi zero, then it would look just like a photon initiated shower. So there's some intrinsic limit about how much rejection of hadrons I can do because of that.
In the one video, the Mexican ranger said that when this project's over, it's going to all be disassembled.
Yeah.
Could it be reassembled someplace else in the world? And might you see different results?
Yeah. So some of the electronics is 25 years old. Some of the phototubes are 25 years old, but some of them are probably still usable. I think the likeliest thing to happen is that those phototubes will get reused somewhere. Members of the collaboration and others are working on a project called SWGO, Southern Water Cherenkov Gamma Ray Observatory, to be in, I don't know, Bolivia, Peru, somewhere in there, at higher altitude still, different design, obviously better. That's why we're going to do it, right? And they might reuse some of the phototubes. It's still always a fascinating thing, shipping things from one country to another and dealing through customs and so on. And who actually owns this? Is it owned by the university? Is it owned by this lab that it was shipped to? Does that mean you have to pay taxes or not? Blah, blah, blah. But there's an intent to try to recycle some of it. Now, the steel, we're just going to sell, right? And the concrete, you have to chop up and haul down the mountain. So there's stuff that can be recycled and there's stuff that is valuable enough to recycle, and some stuff that you'd like to recycle, but probably just isn't going to be. Like some of the electronics, because again, standards change. And so that electronics wouldn't plug into what I build today. But this is sort of, in some ways, a decidedly low-tech experiment in that we're using 20, 25-year-old electronics in many cases, just to save money. Because as I mentioned, we built the thing for around 10 million, which is really low on the scale of an apparatus that can be used by 100 people for tens of years. I know it's still a lot of money, but we got approved because we were cheap and had a good physics plan. And I have to say that I think we even did better than we imagined when we built the thing. Yeah.
Are there certain qualities of the water itself that deteriorate over time and require some sort of maintenance activity?
We have not seen that. That's because we were pretty careful when we put the water in. Like I said, we UV lamped it to kill anything living. We carbon filtered out most of the particulate stuff. And we do periodic measurements of the water quality, basically we describe it as an attenuation thing, but how far a light can go before it's scattered. And that should be of the order of the size of the tank or more. And that still seems to be holding after years. Okay. So I have sky maps. How do I turn that into a paper? So we make the maps. I'll mention that actually we make a bunch of maps. We make maps with different amounts of energy, right? So later on, we can use that set of maps to measure the energy spectrum, okay? We look for statistically significant emission, and those might be new sources, discoveries. That's one of the neat things about this, is that this is such a new wavelength band that we are discovering things that nobody's seen before. So we publish sky maps, we publish catalogs of the new sources. And then the next level is we might take some of those new sources and study them in detail. What does that mean? We look at the physical extent of the source. Some of them just look like little dots in the sky. Some of them have some extended size, and there are conclusions you can draw from that. We measure the energy spectrum of the source by fitting to the energy maps. So you're again characterizing what you learn about the source that you've seen. We compare with maps at other wavelengths and other observatories. There's lots of things known by optical astronomy, right? There are all kinds of interesting stuff out in the sky. The question is, look, out of the trillions of stars in the Milky Way alone, right? What objects produce TeV emission? It's rare. Like I said, the catalog is the entire catalog of this wavelength is less than 300 sources. So it's something which is pretty exotic. And you want to try to see, well, okay, which of these things at their location in the sky, what other things are known at that position? So that sort of limits you to what kind of thing could be causing this. So trying to understand what's going on. We look at sources to see whether they're variable in the amount of emission they do, time dependent. We do detailed modeling at the physics level or at the detector level or the most source fit level to interpret the results. Sometimes we do systematic studies of a class of objects taken together. Let's see what we can learn about the distribution of parameters. We look for transient emissions. So most of what we see is steady sources, but sometimes something flashes on and flashes off. There are gamma ray bursts, for example, and we look for them. We haven't seen one, but I think there have been 2 instances where some other observatories either had better sensitivity than us or was better positioned because it went off when it was overhead for them, not for us. And then interestingly enough, you can also publish a paper when you don't see something. If you phrase it correctly, right? Because what you can do, if you understand the sensitivity of your detector, you can say, what is the limit on how much flux could have been there? Otherwise, I would have seen it. And sometimes that actually is quite interesting. And that's used by theorists to test and constrain their models. So here's a sky map from the first 100 days of HAWC, first year of HAWC. That is the Milky Way. I've drawn sketches of some constellations so you sort of see what's going on. Here are the 3 brightest sources in the sky. One is the Crab Nebula. There's a brightish thing which is sort of near it, which we'll talk about later. If I continued this curve, the Milky Way, it would go down here and then come back up through here. But this is looking towards the center of the galaxy, and this is looking towards the outer part of the galaxy. So there's many fewer stars out in that direction. But the Crab Nebula is nonetheless the brightest thing in the sky. The second and third brightest things in the sky have these funny code names, named for a Russian who discovered them. And those turn out to be other galaxies, which is sort of surprising, right? The second and third brightest thing in the sky is not even in our own galaxy. So that sort of tells you that some moderately exotic thing has to happen for us to even be able to see it. So this is in the right ascension and declination coordinates. The range in which we see is sort of, you can go up to plus 60 in declination and down to minus 20 in declination, or maybe minus 30 nowadays. And now with our most recent improvement, this is the map looking for 2,300 days or 4 or 5 years. Looks the same general shape, but there's more stuff you can see now. Here's one of my colleagues did a sort of interpolation of some other things, so you sort of see what the shape of the Milky Way trace is across these coordinates. The bright area is over here, but there's some action over here. Oh, and by the way, a personal favorite of mine, the Crab Nebula is pretty close to Orion, just above the club, right? Yeah. Most, for steady sources, we use all the data we got. Yeah, it's brighter than, right? Okay. We test to see whether it's steady or not, but we almost always start off with the assumption it's steady and how much you see. If I switch to the galactic coordinates where the galactic plane is horizontal band, then the holes at the North and South Pole get mapped into shapes like this. Okay. The horizontal scale is the statistical significance. So black is brightest. And then this region here where you start seeing red is about when we become interested in the thing. Significance of 4 or 5 or so above. If I zoom onto that galactic plane and blow it up, well, actually we see quite a bit of detail. Here's 2 sections of the galactic plane. And you see all these labels? Those are either our names for sources or other objects that are known to be there. So we're trying to understand what each of the bright spots mean. I'll show you later on a zoom in I think around this region. We are, as I mentioned, a band. This is sort of an old version. Our map looks a little better now. I think this is even from the previous predecessor experiment. But what we're doing here is, if I can look at the galaxy in different wavelengths, right? And they show different characteristics of what's going on in the Milky Way. And what we're doing is we're building a map of what it looks like in the TeV gamma rays. So the task for the next generation is to fill this thing in better. We built several source catalogs, one in 2017, one in 2020. We're working on a new one now. The one in 2017 found 39 sources, 10 of which were new and not seen before. So we had some capabilities to see old things and some things which no one else had seen. The one in 2020 bumped that up to 65 sources, of which 20 were new. And we're now working on the 4th catalog. Should be published sometime this year. What kind of things inside the galaxy can cause that? Number one is something called pulsar wind nebulae. Those are areas around pulsars. Pulsars are neutron stars. Those are what's left over after a supernova. So you first have to have a supernova to make this kind of a source. Another thing was called supernova remnants, which is just the spare dust of the star, which is pitched around into space. So you had a whole star worth of stuff. Not all of it makes its way into the neutron star when it collapses. And so there's a fair bit of material around. And you sometimes can light those up, if they're dense enough, by cosmic rays. So you can see cosmic rays lighting up the remnants, the shell of a supernova, and making light there. Yeah.
I understand we're almost to a supernova that we will see.
Yeah,
And-
Eta Carinii is they're thinking it's working on it. Yeah.
Like within a month,
Something.
something.
Well,
Did I
no,
read that?
there's something I was looking at last night was something called a nova, not a supernova.
Oh,
And this is in fact, this is a white dwarf star with a companion which dumps extra
Yeah.
material on it, and every once in a while the surface goes thermonuclear. And so there's this guy last blew up in 1946, and they're thinking that sometime before the summer it's liable to blow up again. And it might even be visible to the naked eye, and I think some people think it might be even as bright as the North Star. And we are very interested at MSU in such transients, in fact. So we'll go after it, but it's not a supernova. It's only a regular nova, only. Just a little supernuclear explosion on some little star. There's some more exotic objects called microquasars, which I'll say a little bit about. I'll say, so what the Crab Nebula? Crab Nebula is the brightest thing in our sky. It is one of the most studied objects in the entire galaxy because it's a recent supernova, which went off in 1054 AD. And we know when it happened. So so it gives us a view of what happens, at least in some kind of some supernovae, 1,000 years ago. These are, this is the Pulsar Wind Nebula. It has this toroidal structure here. This is the view in X-rays, and it has this. So this is caused by circular magnetic fields caused by the pulsar, that neutron star. This has a very peculiar spectrum, and with two peaks, two big broad peaks, and that's because the electrons which are causing this can either do one of two things. One is they can be bent in magnetic fields and emit X-rays as in so-called synchrotron radiation. The other is that those high-energy electrons can crash into some unsuspecting low-energy photon and boost it up to a really high energy where we could see it. Now, to us, the Crab Nebula looks like a dot. This is just really no bigger than our ability to resolve a point. But it was quite impressive in its time. It was visible in the daytime for 3 weeks, according to court records in China. It's nearly steady. We don't see pulsations, even though it's a pulsar in the middle of it. But we don't see high energy pulsations. But some other people have, and I'm working with a colleague who's working on trying to do that. We use it largely as a calibration source to make sure we know what we're doing. And thus we compare the energy spectrum with other measurements to see what we're all talking about the same thing. Now, near the Crab Nebula, there are some other guys, and those also are sort of interesting. And all three of them are various versions of Pulsar Wind Nebulae. The Geminga and its neighbor, Monogem, are older than Crab by a lot, because they're hundreds of thousands of years old. The X-ray spectrum, a structure that you saw for the Crab Nebula in the X-ray, the little toroidal thing, that's tiny compared to what we could see. And it's also the case for Geminga. But interestingly enough, although this is perfectly visible in the X-ray and is small, in the TEV, it's not small. In fact, it's like 5 degrees across, 10 times as big as the moon, from something which is at its core a neutron star. So that's an interesting question, what's going on. And in fact, we measured in detail the angular distribution of products around there. And we found it quite similar at these two nearby to each other Pulsar Wind Nebulae. And there's all kinds of interesting things happen. You go through the logic and it's very surprising to be that large. What we think has happened is that lighting up is due to electrons which have escaped from the vicinity of the Pulsar Wind Nebula itself, but are sort of hanging around nearby. And so there's some reason that they don't just run away. That can be parameterized by something called a diffusion constant. And the diffusion constant needed to explain this is quite a bit smaller, like a factor of 100, than what we believe by just studies of general cosmic rays, it would be in general between stars. So this is quite surprising. And this phenomenon is called TeV halos, this halo of electrons out here, and therefore those producing TeV photons. And that's a new class of sources which people are starting to study now. We were the first to see them, and we've seen a couple of others. Other experiments have also seen them now that they know hints about how to look for them. Here's an example of a detailed source study. So like here's one region which I showed you earlier. I'm going to zoom into this area around this and this source. It looks something like this. Now we model it. The first level of modeling is just, well, how many separate sources is that? And so we say, well, it's one bright round source and another not as bright round source, and it gives sort of a general glow that looks like this. And well, this is not obviously identical to that, but if I subtract this model from the data, then I look at what's left, and actually there's not much left. So it does a pretty reasonable job, this simple model, of describing most of what's going on there. And you can then try to measure the energy spectrum of the two sources. And something interesting happens. It goes out to quite high energies. So this region seems to be producing protons with well over 100 TeV in energy. And 1000 TeV, or a PeV, is an area which people have become very interested, because maybe you remember last week, there's a little kink in the cosmic ray spectrum and around 1 PeV. And that is felt to be the distinction between when most of the sources are inside the galaxy to when they're outside the galaxy. So if we are generating things up to a PeV inside the galaxy, well, where are they? And so part of what we're doing is looking at places like that. We can do that because, for example, if I see a photon of energy E and it's produced by pi zeros, produced by protons hitting something, then the protons had to be about 10 times as much that energy. So when we see 100 TeV photons, that implies 1000 TeV or 1 PeV proton. And that's a candidate for one of these sources of cosmic rays. Here's a object called a microquasar. And we have sort of the first example of that. So let's see, I think I had, yeah. So the idea is I have a giant star and a black hole near each other. The black hole is taking material from the atmosphere of the giant star, it puts it into accretion disk, and a lot of the information of the material goes into the black hole. But black holes are sort of sloppy eaters. And if the stuff is in the accretion disk and doesn't go in, it winds up, by the wonders of quantum thermodynamics, hydrodynamics, produce jets that go off perpendicular to the accretion disk. And those are rather like, they're like quasars, in that quasars are felt to be galactic-sized black holes with big accretion disks. And this is sort of a micro version of it, because this is only a star-sized black hole. So it's a very interesting system. And again, we measure the spectrum, and we try to see what's going on. So here's the bright source, and here's the dimmer source. And if I blow that up one more time, I see two bright regions, and X marks the spot where, by other means, people think that is the location of this microquasar, the black hole in the star. So they're producing jets which are running off in opposite directions, then run into material and light them up. And again, we were the first to get a good clear view of that. Some other experiments have looked at it before. They've looked with better spatial resolution and they said, yep, nothing happening at the location of the black hole. Not in this energy range. It's not, there's nothing happening, but it really looks like that, yeah, the jets go out here, hit the clouds in here, and so that's what's going on. And they go out to quite high energies. And again, that's a bit of a surprise that this system was able to accelerate things again up to a order of PeV. So again, a bit of a surprise that that could accelerate things to such high energy. I'll just flash that we do see evidence that we can see the galactic center in TeV gamma rays. That's new. We're just gotten to where we can barely do that. We also look at very high energies. So I'm going to show you a series of maps with different cuts. Here's what, remember you saw the galactic plane with lots of complicated things going on. Here's the same regions, but saying I'm not interested in anything less than 50 TeV. It cuts out a lot of things, but there are sources left at 50 TeV. 25 of them, in fact. It also says that most of the sources that are at that high energy are not point sources that are extended. So that's something also another subject for further study. Why is the region so big? I jump it up to 100 TeV. I still have 18 sources. And again, still extended in size, unlike the crab. And even 170 TeV, we still have a number of significant sources. So we're using our ability to measure high energies and see 4 significant sources. Quite interesting. Again, what's causing those guys? Remember, 177 TeV photons probably means more than 2 PeV underlying acceleration of charged particles to do that. Either electrons or positrons, electrons or protons. We can do spectra of those things at the highest energy and again, see how far out they go. And I just mentioned that at least until just this last year, HAWC was the premier high energy instrument in the entire world. Not chopped liver. Not bad for 10 million. There are similar things to those microquasars at the center of some galaxies. Remember I said the second and third brightest thing in the sky was another galaxy? It's because there's a giant black hole here, produces enormous jets. And as I mentioned last time, if that jet points right at you, it's really bright. It's a fluke that it does that, right? But if it does, it's bright. And here's a picture in other wavelengths of such a system. This is the size of a galaxy. This, much, much larger than the galaxy, is the pair of jets and the interaction region at the end of the jets. Some really, really high energy phenomena going on. Again, associated with the action of black hole and how rotational energy gets turned into acceleration. Oh, that was the first sky map. Oh, I'm not sure why this is in here. Oh, yeah. Let's just remind you, this is where the Markarians were. Markarians are far from the galactic plane. So it's not too surprising that they're really not in the galaxy. The only way something could be this far off the galactic plane and inside the galaxy is if it was really quite close to it. But we know where these guys are, and they're a long way away. Yeah.
But you're showing us a two-dimensional map, and you're suggesting that comparing 4.1 and 5 with it tells us nothing about how deep into the space. So they're not really in proximity of each other necessarily.
No, they aren't. They're not. They have different redshifts. I mean, they have redshifts of like 0.03, 003, or something like this. People can measure pretty decent estimates to them, even though it's too far to do by parallax, right? So they do that by looking at details of the spectra. And there's this general phenomenon that there's something that objects which are far from us or receding from us, receding things like train whistle shifts the frequency. So when they measure the spectrum detail, they can come up with an estimate how far the thing is. So that's how the depth's done, not by us. It's by the fact that these are physically coincident with objects which are known by other reasons that allow us to make that interpretation. You really have to put the whole picture together. One of the things we do is monitor 421. Sometimes it's brighter, sometimes it's not. There often are coordinated campaigns in various places when say, hey, the thing's really bright, send out an announcement, everybody does measurements, measure the spectra, see what's going on. We also search for transients in the other one. And an interesting thing is if I have a time variation on the sky-L time, that must mean, just by causality, that the size of the acceleration region which is doing that can't be much bigger than c times that time. So for example, the Earth is 8 light minutes away from the sun, right? So if you see temporal variations in a source like this that are of order minutes, then it's a really tiny region. It's a solar system region, size region, not a galaxy size region, which is doing this. Those jets turn out to have lots of complicated regions, and that's part of what goes on. They vary in all kinds of different timescales. We can do some other fancy things with that by extrapolating the spectrum and looking how much is absorbed by the light, by collisions of TeV photons with light between here and there. That's a complicated but interesting analysis. And one of the last things I'll look at is turning something to nothing. Again, if you understand your sensitivity well enough, then not seeing something can be turned to a quantitative limit how much could have been there. Right. And the example here is taken from one of my student who's now at Google, his PhD thesis. We worked with Humberto Martinez, who is a graduate student in Mexico. For a couple of years, he would give presentations. We couldn't understand what the hell he was talking about. But eventually we got through. And he is working on areas of theory related to quantum gravity. And interestingly enough, in quantum gravity, there can be maximum energy at which light propagates successfully. I'm not going to go into the details of why, but if we see light at a certain energy, then Emax has to be bigger than that, right? So if we see very energetic stuff, which we do, then that allows us to push up where the maximum energy is. And we did that in some cases by up a factor of 100. We used new technology. Sam also developed the neural net energy estimator, which allowed us to do spectra up to very high energies accurately. And so he combined those two things. He also combined several photon lights for sources and did a joint analysis of them. Again, the example of you can learn extra things by considering a class of things together and collectively analyzing them. And in fact, again, for certain parameters, we pushed the limits as much as a factor of 100. So that made a big splash in the physical review letters. I said we touched Einstein's halo because this is Lorentz invariance violation. We got like hundreds of citations in the popular press. Gizmodo also wrote an article about it, about this publication. And the way it works is here's spectra that we measure in the solid lines. And if you put an Emax, well, the thing would have to fall off. In principle, the physics would say it would fall off instantly, but that never quite happens because we have energy resolution, right? But anyway, that's what the spectrum would look like, the dotted line, the dashed lines, if there was a maximum, and that's not what we observed. So again, by statistical analysis, we can say, well, Emax has to be at least as big as this, and that pushes the limits quite a bit. Okay, future of HAWC. We're probably going to be funded maybe 2 or 3 more years by the National Science Foundation. At that point, we have to tear things down. We will still, some people will still continue to analyze the data. We will also probably make the data public. What we can't analyze, we can let others analyze. Again, if we have enough support to actually house the data, because this is like 10 petabytes of data, or we have to do some extraction of it. The LASO observatory in China has better sensitivity than us. It was rather directly developed from early HAWC plans. There was an eerie resemblance of the plots we had made with our software at Los Alamos National Laboratory and some of the initial plots that they made. They had a bigger budget. So they built what we wanted to build, which is a lot bigger than what we built, and more. So it's now in the northern hemisphere for high energies. It's the king. That's another reason why we should limit how much more longer we run. We're doing complicated white papers about, well, what do we gain by running for how long in our discussions with the National Science Foundation. So that's going to be a considered decision. Another thing which is important is, just as LASO learned from our plans, the next generation detector can learn from not only our plans, but what we learned by operating this detector. Yeah. Unclassified. It was a trip doing unclassified research at Los Alamos. All my colleagues who you saw from Los Alamos have security clearances. Some of them spend most of their time almost blowing things up. And this is in 2003. You were not allowed to have wireless on your laptop for security purposes. There was a little truck that would go around with antennas listening to see if you had any wireless around here. Shouldn't be. So it's an interesting environment. And so it's going to be applied in other detectors. Gordon asked me about applications. Well, that's a tough one. This is very much basic research. We're trying to figure out what's going on, things that we have never seen before. That's the guts of the matter. We study behavior at energies which cannot be produced anywhere on Earth. And in fact, some of the things we study are it's not even clear in the conceivable future how close we could get. So there's not going to be a gamma ray transistor, okay? We study objects which are not here in front of us, but that's the only laboratory we have to study them, study behaviors of microquasars. So the goal is new knowledge, and I try to share that with the public. The immediate applications are, in fact, to adjacent fields of study, like astronomy, like high energy physics, like cosmology. So our results get reinterpreted by adjacent fields and used to constrain the things that they are thinking about. I would also say that most of our PhD students wind up in industry. In fact, I've had a couple of students who I think were capable of becoming staff faculty members, but none of them ever did. So some of them own their own companies, some of them are data scientists, so on. Now, I think we really, really do some very good things for these students, and as by inference, for society. Here's things that they learn when they work with us. They have excellent training in scientific thinking, advanced computing. We deal with large, complicated data sets. They have familiarity with advanced electronics. They, during their graduate career, develop sophisticated mathematical skills. They wrestle for months at a time with complex problem solving. They develop perseverance, whether they had it or not. If they're finished, they needed perseverance, trust me. They become quite well versed in statistics and data science. A rather important thing is they develop critical judgment of whether the data they're looking at is valid or not. Just because a computer writes some number down doesn't mean it's the correct answer. You yourself might have screwed up in what you told it to do, might you not? We require international teamwork to do this work. You know, some of the more famous scientists are indeed in the US, but not all of them. And we could not operate without the sponsorship of the Astronomy Institute in Mexico, which organized the site. Alberto Carmagnana, in fact, was the director of Innova when we started the business. You have no choice but to develop precise writing and editing skills. Like it or not, you have to get to the point where you can deal with constructive feedback and make something out of it, which doesn't happen just because you happen to be a graduate student. Requires practice. We develop public presentation and speaking skills. At least I hope you get a decent job. And you learn to critically read material and extract information from it. And one general important thing is that you become at some level fearless because you're working on really hard problems. Just because somebody wants to know, well, okay, does changing the placement of this thing in the gross value improve sales? Well, that's okay, fine, that's interesting, but it's not harder than what I've worked on. And a senior data analyst I know in a pretty sizable company in the US says he much prefers PhD students from science when you're talking about industrial data science jobs over people with specialty degrees in data science, precisely because this set of skills that they've developed. So reference for further study, I've passed out a list. I think this has been emailed to you as well. It includes some of the videos I show, so you can share them with your friends. I highly recommend this book, which got me started on the subject of astronomy when I was in high school. There is not only nice view of constellations, but also coordinate systems, precession of the equinoxes, all this stuff is nicely explained there. He's a very visual guy, does a great job. The Gizmodo video, and another, if you do this Google search, you'll find their description of the Lorentz invariance violation paper I was intimately involved with. There's a nice Symmetry magazine article about how Brenda Magda and her Mexican colleagues made HAWC to appear in Mexico. And there's also I think you saw a little excerpt of it, but there's a time-lapse photography video of HAWC construction that they have there as well. It's fun to watch. If you want more detail, here's a professional publication on the 20, 30 pages on the HAWC main array. It's monitoring how lots of parts work. You'll find detail about the water in there, the whole 9 yards. And then I just picked one example of a short presentation of what SWGO might look like. We'll probably make it, instead of one tank, we'll have a 2-layer tank where the bottom part will be specialized in detecting muons. So they'll be looking at something like 5,000 feet, but they haven't decided yet whether they're going to build the tanks or they're going to put it in a lake or what. The early days. Okay, thank you. I don't know if Gordon will let you ask any more questions or not.